So our goal in this video is to use R to do prediction in a little bit easier way for us, as well as allowing us to get a confidence interval around our estimated probability. In addition, we'll close out the video by determining which of our models actually seems to be best for our data set presented here. So first, let's talk about an easier way to predict. And I'm going to use this right now just for the clog-log model. Keep in mind that the process would be the same regardless of which model that I'm using, just keeping in mind that when I do this, I'd make sure I'm using the correct alpha hat and beta hat to do it. So the first thing I'm going to do is actually just predict data for just a single observation, and here we're going to work on our distance of 20. I'm going to call my data just predict.data. Again, this is what I'm naming it. And I'm going to create a data frame, basically a data set, with just one variable and one value inside that one observation. Then I can use the predict function. The object that I want to use is my mod.fit. Now the mod.fit then that I am using is my one where we've used the complementary log-log link. So I will want to make sure that I've run most recently the one here with that complementary log-log, and I've named it that mod.fit. So that's why that's going to be important here for us when I actually use my code to do my prediction, because it's going to be using that object. The new data I want to use for prediction is what's inside my predict.data, so notice how those match. And then I'm going to use what's called type equals response. Just for comparison, below I'm doing the exact same code where the difference is I'm using type equals link. And you'll notice here that we're actually going to get two different values, and let's explain what those technically are. So let me run that here for our data. So there's our response output as well as then our link output. And so what that is doing differently is it depends upon which one we're looking at here. Sorry, my picture's a little bit behind my actual screen. So what we're looking at is the link versus response. So I look at my two different models I have here for the complementary log-log. This first one is what we refer to as the link part, versus the second part would be our response part. So that's the link versus that pi hat is going to be your response. I apologize for that interruption. My iPad and stuff is not cooperating as well as useful, so I apologize that you're seeing me have to refresh the window quite a bit here. So again, so the first one is the link, and then the second one is the response. So when I look at this output I'm getting, the response is generally going to be the one I'm really interested in because that's going to give me my pi hat. If I use that link function here instead in my predict model, that's going to give me what this value is, which is really not all that useful to me. So kind of my moral is the response is going to be a much more useful way for me to do this. Now looking at the next part of the code here. Oh, wrong way. There we go. This is now predicting for more than one distance at the same time. So here I'm trying to do the 20 yards and 50 yards at the same time. So I'm just calling it predict.data 2 so that it's different than the one above. I'm again creating a data frame, and I only want one variable with both the numbers of 20 and 50 inside of it. So just that C is for me to combine them, comma to separate my different values. Now for this one, I'm only going to use the response for the reasons we just discussed, that the link is not very useful for me. And then it's going to give me my two different values, and they're going to be in the order listed in my data frame itself. So if you put 50 in first and then 20, that's also the order it would spit those out in. So if I look at my predict.data 2, this is my new data set. It just has those two observations inside of it. And now I'm going to predict for that data using the response so I get my pi hats for those two values. Why the prediction function is also going to be useful for us is it can also let me find a standard error. The reason why I need a standard error is that's what I need to create any confidence interval that I'm working with. So what we're going to do is we're going to be looking at a very similar type of code. I'm still using that predict data 2. Because I'm going to be doing a confidence interval, I'm going to set my alpha level here as well. And I'm going to now do this predict function, but I'm going to save it in something so that I can actually create an interval using it later. The only thing I've added to this is this extra part where it says se.fit equals true. What this is going to do for me is it's going to create those standard errors and have them stored for me so that I can use them. Okay, so we're going to create the standard errors and then store them. So let's actually just run that so we can see what's inside this save.pi hat. All right, so if we look at what's inside our save.pi hat, make this different size so you can actually see it a little bit. So it has like our different values here inside of it, those estimated probabilities. It's also stored these standard errors in it, so I actually do have these numbers that I want as well. So that's what's kind of inside here, just up to here, inside that save.pi hat. So then I'm going to create my confidence interval from there. What I'm going to do here is what I would refer to as like a basic walled interval. And so what I mean by a basic walled interval is we're basically just going to take our pi hat plus or minus our z times our standard error. So our pi hat, we already have, we found those values when we predicted. That was part of what we get. So that's going to be called the fit inside of this new data set I've created is the fit. The standard error I'm going to be using, so I'm creating this data set here. Got off. Save.pi hat, $fit is my pi hat. My Q norm here is going to get me my Z. And then this is going to pull off that $fit. Same thing in the upper with just that plus sign instead of the minus sign there. Now I'm just storing this all so it prints a little bit nicer looking. So creating a data frame that has my original data I was predicting for, my estimated probabilities of success that I already have in here as well, the standard error just so I can see what those values actually were, and then my lower and my upper. So when I run that code, and then run my data frame, here is the same output that you see there. So you'll first of all notice that the standard error is different for the different distances. There's a larger variability for larger distances than that shorter distance that we see here. We're also given that confidence interval of that lower and that upper. So then kind of getting us to understand where one of these numbers is coming from. So this 0.9864 is coming from taking our pi hat, which was 0.9774. Since it's the upper, it's going to be plus. Our z is based upon that alpha of 0.05, which we've kind of learned is a z of 1.96, times our standard error, which is that 0.0046. So that's where that number is coming from. And again, so the standard error being different is not shocking to me at all, especially we've already talked for the binomial distribution that the variability actually does change based upon your value of pi as well. So I'm very much not surprised that I have different standard errors. I'm also going to have a different standard error based upon how much data I have at the different distances as well. So that's not going to be shocking here as well. finally, just to understand what we're going to try to figure out which model fits best, I also want to look at all of my models over that bubble plot that we created in a previous video. So first of all, here is the plot. So it's the same bubble plot that we've seen before, but now instead of just having the logit function on it, I've graphed the complementary log and the probit as well. So all three of them are there. So the main difference here, what I'm doing is before we just had a one line for the logit, and instead of having now 3 lines to put them all on there, I'm again using that legend where I can locate where it is so that it's not automatically there for me. So let's go ahead and run all of that. And so here is our plot that we get. Of course, you can, if you need to, try to change the size here and stuff to make it look a little bit nicer so you can maybe see it a little bit better. So here is our plot that we get. So what we can probably see pretty easily from this plot is that all 3 models are kind of staying about the same here for the early distances. It's for these larger distances that we start seeing a little bit more variation. And it's really very hard to see which ones really fit the data better because I have very, very little data out here. So where there's really those big differences, there really is not maybe a good idea of determining what fits the data best with such limited data that far away. So what I can see here is for those large distances that the logit's going to estimate for the smallest probability of success, where the complementary log is going to have the highest estimated probability of success. So maybe if I'm a more conservative football coach, I might want the red one because I'd rather underestimate my probability of success than possibly overestimate it. Versus if you're a more glass half full type of person, you might want the green one instead. So we can kind of use that based upon perspective to decide which one fits the data best. But one of the things that we really wanted to do was to figure out, well, which of our models did we like best for our data? So the things that we talked about that we could use to make this decision. My first idea is, would I know that things are already normal? I don't know if the normal transformation is the best one here, so I don't really know this one. If I already knew something about feeling normal distribution felt comfortable, then the probit would sort of be my way to go. We sort of discussed looking at the model on the graph here to determine which one seemed to fit the best. Again, I probably say they all fit pretty similar early on, and then mainly those differences the further for those larger distances. So is there one that fits best? I definitely think that's going to be pretty subjective here, telling which one, not that it isn't always subjective, but it's very subjective here because of really their big differences being here where there's very, very little data to really determine which one is actually fitting the data better. So one thing that we haven't talked about that I mentioned before is that we can look at this thing called AIC. And the AIC does get spit out in our outputs. I'm actually going to show you in our notes instead of going to R. For each time that I fit a model, so for example here for the complementary log, you'll see here toward the very bottom, there's this thing called this AIC. And so what we can do is just write down the AIC for each of our models that we got. All right, so for my log, it was 784.2. Looking back for it when we ran the probit, it was 787.03. And then finally, way back early on, when we ran it for the logit, it was 791.1. So if I were to just look at the AIC, it appears here that the common log would have the smallest AIC and would give me good reason to use it. So if I really maybe didn't have anything else to look at, looking at AIC can help me give some justification for the complementary log. However, finally, if our main goal is being able to interpret the model, not just doing predictions, but actually interpreting the model, that would tell me that I would want to use the logit link function. So all three are perfectly valid when your main goal is prediction. If your goal is more to do interpretations, the logit is going to be a much smarter way to go. And so that's why in the next set of notes, we're going to focus looking at just solely the logit link function and doing what's called logistic regression, because it's the most commonly one used because of its nice interpretations. So this should end the generalized linear model notes here for you. If you have questions, whether it's on code, whether it's on interpreting the output, if you're just having problems creating the plots, please let me know what kinds of questions that you have. Do make sure that you can find the estimated probabilities by hand, that you understand how to create that confidence interval that we just looked at using the standard errors to help us actually create that as well. But again, please let me know if you have questions. Post on discussion boards as needed. Attend Zoom things as you need as well, please.